This is CNET 125, CISSP, and what we're doing today is the second part of Net Plus, which is just a whole bunch of networking facts zipping by kind of quickly as last time. So we left off partway through this chapter 4 slides, and I'm going to pick up where we left off. This is a one-chapter review of the Net Plus certification, essentially. And, oh, this is the wrong one. Whoops. It's this one. There we go. Come on. There we go. Oops. Come on, come on. There we go. All right. So, T1 lines. You rent them from the phone company, and then you have a point-to-point dedicated line of your very own. At one time, they were actually, I think, 23 pairs of copper wire. Now it's all done with software and fiber optics. But anyway, that gives you 1.5 megabits per second circuit between 2 points, or T3 gives you 45 megabits per second. Or you can move up to bigger ones. E1 and E3 are comparable ones, and there's optical carriers to get bigger than that. Anyway, those are common point-to-point carrier lines you'd buy for dedicated lines. Sonnet is the one that gets really big, that goes up to gigabits per second, and this is what you would buy if you're really a huge internet consumer like an ISP or something. And another thing you could do is use frame relay. Frame relay is a pretty old protocol, but it lets you take a line with a high bandwidth and cut it up into chunks and sell the chunks to different customers, so they get virtual circuits, so you get a portion of the bandwidth on a line. Permanent virtual circuits are always connected. Switched virtual circuits keep changing and throwing the connection when needed and breaking it again. And then there's X25, which is a really old one. It's been obsolete for decades. I don't think anybody's going to see that very much anymore. ATM is still used a lot. You have 53 byte cells with 5 bytes of address on each one, so these packets are very small and they move very fast, and there's gaps between them. There's plenty of opportunity to interlace other traffic between them. Multi-protocol label switching is another way to make wide area network forwarding, and it can carry many different types of traffic. These wide area network protocols, there's quite a few of them, and they're different than the ones you use on local area networks. You won't see them unless you're a big data center or an ISP. Then there's synchronous data link control and high-level data link control, which are another way to move data on the wide area network, and most of these are layer 2 protocols. They don't use IP addresses. They just use an address like MAC addresses, because typically they're just on a line going from one point to another point. They don't really have any routing decisions. At most, they have a little switching to do. HDLC has these 3 modes: normal response, asynchronous response, and asynchronous balanced mode. And this is for converged protocols, which has been all the rage for the last 15 years or so, where you try to move all your data traffic over one line. So your telephone calls, your video, your email, and everything go over one line, and therefore you have many different kinds of traffic interlaced on the same trunk lines. So distributed network protocol is one used by the energy sector to connect SCADA and smart grid technology together. And it can be carried over TCP/IP, and it has, like all these protocols, had various versions. They keep getting more secure. Now it's got secure authentication that fixed its vulnerabilities to a lot of problems, and now it supports the public key infrastructure, so it's like HTTPS. And then there are storage protocols. In modern large data centers, you do not have one drive connected to a CPU. You have a whole storage area network with many devices networked together, and then you have processing done elsewhere. And so the storage needs to have a networking protocol just for the storage devices to talk to each other, to figure out who stored that block of data and where it is. And so here's some of the protocols they use. Fiber channel over Ethernet is a big one. iSCSI, and these are ways to make a whole cluster of servers running many drives appear to be just a single drive to another machine. All right, and so fiber channel over Ethernet does not use fiber optics, it's just called a fiber because it's a pattern of many parallel wires that looks sort of like a fiber in biology. And so it uses special cables, special hardware. You can run it over standard Ethernet, but not TCP/IP, or you can, in fact, run it over TCP/IP. You can do it various different ways. And iSCSI is another way to do it. It can be routed so you can move your traffic over a WAN. The others are typically done just in one physical room in one data center. You put all your hardware, your data servers all near each other, but you can have them distributed over a wider area network if you want to. And then there's virtual story area networks, like a virtual local area network, another way to combine your database servers to form a virtual hard drive. Then there's voice over internet protocol, which is what almost everybody's using for phone calls now. If you have a landline phone at home, it's probably not using this, but if you have one at work, it typically is, because then you can have all these automated features like press 1 for this and press 2 for that, and automatic forwarding of voice calls. Although now that everybody's working at home, I'm not so sure how it works. But anyway, this is what happened in all the office phones over the last decade or more. So real-time transport protocol is what actually carries the sound and the video if you're making a video call. Session initiation protocol is what does the session setup, like ringing the phone and telling if you picked it up. And secure real-time transport protocol is a way to provide confidentiality, integrity, and authentication to the system for the secure version of real-time transport protocol. A lot of voice over IP is sent unencrypted, and you can sniff on it, spy on it with Wireshark. That may have gotten better lately, but I know as of like 8 years ago, it was common that people turned off the encryption to get better performance. So the point of this is they say it saves money because you don't need a separate network. The people I know that actually install this stuff say this is a marketing lie. You don't actually save money, but what you do is you get more features that you really want. Like you can just press a button and say forward this to my home phone because I'm going to be home for a while and all that. You have custom messages and everything, and those are what's really valuable. Anyway, software-defined networks are here so you can define how the devices are going to be connected with things like virtual local area networks and all these other virtual networks. So now the physical wiring of your network is separated from the logical wiring, and that's what software-defined networks are. OpenFlow is the most well-known SDN protocol that allows you to control these switching rules, and it is a modern protocol with encryption for the traffic. So that's wide area network stuff. In a very simple high level, like I say, the CISSP is a mile wide and an inch deep. All you really need to know is to sort of identify those terms. Physical separation of wiring. But the point is, it used to be that if you wanted to have a local area network, those computers all had to be in the same room or adjacent rooms, and they all had to go to the same switch. But now you can have a virtual local area network where you choose machines anywhere in your network and just say, I want them in a local area network. And that's an example of software-defined networking. And you can do many other things also. So you make the logical network different than the physical network. All right, it is this one here, 4F. That's the whole wave of the future. Everything is virtual. You're not tied to the physical layout of anything. I'll give it a few more seconds. All right. I guess that's it. So, which link goes up to 45 megs? Yep, that's a T3. We used to call that a high bandwidth, not that high by modern standards. All right, which was the storage protocol? All right, fiber channel over Ethernet. I'm going to stop the stream and restart it because the lag is really bad. Let me see if I can get a better connection. I'll be back in just a few seconds. All right. Yeah, that's definitely much better. Okay, so all right. So what protocol is used by the energy sector? Oh, there should be audio. Do other people have any audio? Okay, good. Thank you. Yeah, I think there was just a few seconds there when I wasn't talking, that's all. Anyway, this DNP3 is for the energy sector. All right. All right, and what's the SDN protocol? All right, open flow. All right. So, they'll have to tell me who they are if they want points. I know who that is. And I don't think we know who. All right, so two of those people, we don't know who they are. Haminsky and Hammy Me. So they may not care, but you won't get points unless you tell me who you really are. Hammy Me is the same as Hammy You. All right, and that might be something I have from before. All right. Got kicked out the first questions. Well, somehow you made it. All right, so let's go on here. So, then wireless networks. Wireless networks have some intrinsic problems. One of them is that there's a de-authentication frame which does not require any password or anything. So there's a denial of service attack where you send out deauth frames and it kicks everyone off the network. And I've never heard of any defense against this, which is one of the flaws. Of course, you could also just start a noisy motor and make a lot of radio frequency interference, and that would have the similar effect of shutting down the wireless network. So wireless networks do have a high error rate due to interference in the radio and electromagnetic spectrum. So there are bands you use that are available for general purpose, and all these consumer devices, including wireless networks, use the same bands. The most common ones are 2.4 and 5 gigahertz, and they're very crowded with a lot of traffic, which creates a lot of interference. So there are techniques to bust through the interference. One of them is frequency hopping sped spectrum, where you keep changing the frequency in a pattern. Then direct sequence is another way, and orthogonal frequency division multiplexing is where you have multiple channels of data sent with different radio signals that are carefully designed so they will not interfere with each other. That's why they call them orthogonal. So here's the generations of Wi-Fi. 802.11n is probably the most common one you'll see around these days, Wi-Fi 4, but some people are moving up to the AC or the AX, called Wi-Fi 5 and Wi-Fi 6. And the next one that is supposedly coming pretty soon is Wi-Fi 7. And 6E and 7 are now moving into the new 6 gigahertz band. So they should be a whole lot faster again when that stuff becomes commonly available. So your wireless network card has 4 modes it can be in. Managed is the only mode a normal person wants to use. The rest are used for special purposes, primarily for hacking into wireless networks. In a managed mode, you are a client and you connect to the wireless server, which is the router, and the router just orders your client what to do. The router says, I am on this channel with this kind of encryption, and you better do that. You just obey what your master says. That's managed mode. Master mode is what the access point is doing. It's sending out to everybody who cares specifications. Here's the conditions you must satisfy to join my network, and people do that. The other two, ad hoc, is one you can use to make a wireless network between 2 clients without a server. So it's not getting you on the internet. You might use it to exchange data between 2 laptops, like a crossover cable. And monitor mode is the equivalent of promiscuous mode in wired networking, where you listen for all network traffic, even if it is not directed to you. So you're sniffing packets that were being sent to other people, like in a coffee house. And therefore, it's something that's useful for hacking into networks and stealing traffic, but doesn't have much of any legitimate purpose. All right. The wireless networks identify themselves with broadcast packets that include their SSID, which is the name of the network. That's what you see in your list of available networks on your laptop, like Google, Starbucks, and so on. You can disable these broadcasts, which prevents you from appearing in this list, and therefore might stop some casual users from connecting to your network, but they could still find your network and connect other ways, like sniffing on it with Wireshark. So this is a very weak security measure. There's another weak security measure where you just filter people by MAC addresses, and you only let through the known MAC addresses. Now, this does prevent casual users like your neighbors from connecting to your network when you don't want them in there, but it doesn't really block them very well, because they could just sniff and find the approved MAC addresses and then spoof them because they're sent unencrypted. Does the SSID look the same if you use a VPN? Yeah, it's at a different level. So your VPN wouldn't kick in until after you get connected to the internet. So the SSID connection happens really at layer 1. And your VPN is at higher layers. So your VPN will not be relevant here. It's a good question, though. What a VPN will do is, once you are connected, then even if somebody sniffs your packets with monitor mode, they will not be able to read the packets because they don't have the key to get into your VPN, unless they also hack your VPN, which is another difficult task. Good. So MAC address filtering will stop some people from getting on your network, but it's not a very secure way to keep them off. WEP was the original one. When wireless networking became popular in the 90s, they had trouble selling the first generation of wireless cards because average consumers said, that can't be safe. My traffic is just going all over the place. So they created this thing called wired equivalent privacy and said, this will make your data as safe as if it was on a wire. And this was an encryption protocol sloppily made and it turned out to be enormously unsafe to use. There were many flaws in it. It was easy to hack into. So that was WEP. And cracking a WEP used to be a common exercise in hacking, in ethical hacking classes. Doesn't matter much anymore because almost nobody is still using WEP. The only people I know that use WEP are people who bought hardware 10 years ago and they're still using legacy hardware. 802.11i is the upgrade, WPA2. And where's WPA? Okay, good. So WPA2 came out like 10 years after WEP was known to be shot. So eventually there was an official way to improve it, which is WPA2, and this is much better with very strong encryption and no known attacks that really break into here. WPA was a temporary stopgap because there was a period of many years when WEP was known to be unsafe, but the IEEE had not made an official protocol that was safe, so the manufacturers just invented this WPA thing, which was just a quickly made patch on WEP. It is just WEP, but it keeps rotating the key, so you can't collect a lot of packets with the same key, and it had 4 adjustments to block the specific attacks, so it was considered a temporary, probably not very secure protocol, but it turned out to be very good. It turned out that there were no significant flaws in it, and the point is you could run it on old hardware that was designed for WEP without upgrading the hardware. It was a software patch. Anyway, WPA is a whole lot better than WEP, and WPA2 is even better. And both WPA and WPA2 are pretty secure. Bluetooth is, of course, very common now to connect to your earphone and speakers and all sorts of things. It had early versions that were slow, and it got much faster, and the earlier versions were a lot less secure too. It used a stream cipher that was very weak. It had an auto-discovery feature that was real risky. It had a negotiation feature where you could negotiate the length of the key down to 8 bits. It had a lot of security problems. Later versions got better. RFID is what you use for these touch things like Apple Pay and the tags that you put to find things. And so there's active RFID where you have a battery and broadcast, semi-passive where you have a battery but you also take some power from the reader, and the passive ones like your credit card where the reader provides the power and your antenna picks up power from the reader and then uses that to do a calculation to perform a sort of challenge response. And that's radio frequency ID. If you want to block any of these radio traffic, you use a Faraday cage. You can wrap a device like a cell phone in tinfoil or put it in a paint can. Any kind of metal container blocks the radio, and you can just wrap aluminum foil around it too. Or the original one was just a wire mesh. You'd put a wire cage around things, and that will keep all the radio from passing in. All right. So 4G is here. Well, Hammy, I see you've won before, but I'm not sure we do know your name. I'm not sure you'll be getting points for winning. If you want your points, you'll have to give me something close to a real name. Unless that is close to a name and it's not obvious. My grader has told me that this class in particular has quite a few people who don't appear to be officially enrolled, which may be true. Everybody's welcome, but if you're actually a City College student and you want points, you have to give me a real name. That's all. I think probably some random people that are not enrolled are coming by trying to get the CISSP, which is a good thing to do. You're all welcome. That's certainly a good thing to do. And I think a lot of people getting the CISSP do not care about getting City College credit. They probably already have a degree. All right, looks like we got everybody. All right, so connecting two devices together like a crossover cable. Yep, that's an ad hoc network, they call it, in the world of wireless. Okay, simultaneous transmissions that do not interfere with each other. Yep, that's the orthogonal frequency division multiplexing. All right, 5 gigahertz only. Which turned out to give it a short range, and it wasn't very popular. Yep, that was the original 802.11a, which was not a hit. All right, what technology blocks radio signals? All right, that's the Faraday cage. All right. All right, that could be Judy or Jordan, and there are 2 Jordans. So once again, you'll have to give me more information if you want to make sure you get your points. Haminsky has won twice, but we don't know who it is. And Hammy Yu has won twice, but we don't know who it is. All right, anyway. Yeah, nice. Another AWS summit, huh? I've been to some of them. I didn't know there's one coming up, though. If you do go to it, it's worth extra credit. Any kind of training event like that is good. All right, so secure network devices and protocols. Here's some hardware stuff. So at layer 1, you can just have cables connecting things together, and then they had repeaters that will just put repeaters in just to make cables stretch a longer distance. And then hubs, or multi-port repeaters, which are pretty much extinct, but this was the original way you'd network things together in the 90s and the early 2000s. Each packet sent into the hub would be repeated to every device, so your device would get a bunch of packets that were not in fact aimed at you. I see it's Judy. You good? Good. Thank you. Anyway, so these were cannot send and receive simultaneously, and all the packets go to every device. So they created a lot of collisions, and you'd have to have retransmission of collisions. Bridges were things that would connect 2 networks, and this was a smart enough device to memorize the MAC addresses on one side and the MAC addresses on the other side. So when it got a packet, it would recognize if that frame, I should call it, if it gets a frame, if it recognizes that frame is going to computer 3, it leaves it on this side. If it recognizes it's going to one of these, it sends it over the bridge to the other one. So this was a bridge between 2 networks. Good. I also see Hammy telling me who they are. That's good. Good. All right, good. And So that was the original bridge between two networks, and the thing that almost everybody uses now is switches, which is a multi-port bridge, where instead of just having two directions, it has many ports, and it learns what the MAC address is on every port after it gets the first frame, and after that it only sends frames to the correct location. So if you have a switch network, you will not receive hardly any frames that are not intended for you, which is a nice thing. That prevents collisions and makes the network faster. VLANs, which we were talking about before, is where you would take, an original LAN is this. You'd have computers that are near each other, all connected to the same switch, and then they're on a local area network where broadcast traffic will reach all these devices. But if you want to have a separation of devices on your network that's different, then you can have virtual local area networks where you call these devices one VLAN and these another VLAN. And if you have a broadcast from here, it only goes through that part of the network. And that's what I was saying before. This is the beginning of software-defined networking, where you now have a network segment that is defined not by the physical wires, but by labels you put in the software, which is very nice. Now you can have like a high security network where you don't want it being on the same local area network as a low security network, and you can assign those devices on either network with disregard for the actual physical location. All right. And another issue is port isolation. One way pen testers like to break into networks and other hackers is they get into the building somehow, and then they just pull out a laptop and connect to an unused port in the wall. VLAN only stands IP or can understand MAC. VLANs work by MAC address. They work at layer 2. They are not using IP. Therefore, technically, they extend Ethernet to have an extra label called the VLAN label in it. Some people think of them as like layer 2.5. It's a good question. So port isolation is where you can specify what devices are able to connect to a port. And you can set it to memorize the MAC address of the first computer that connects, and if anything else tries to connect, block it, so people can't pull out a plug and plug in another device. Now, port isolation is another issue. If you go to Starbucks, you'll see this. If you connect to the Starbucks network, and you're in a room full of people using laptops, if you try to run like a port scan, you'll see that you're the only person on the network. It has isolation turned on, so every customer that connects is put on a separate VLAN. So if you are like doing file sharing or something, other customers will not see your file shares and be able to connect to them. So that's port isolation. Span ports are ports intended to collect all the traffic. Now there's one case in which this monitor mode makes sense, and promiscuous mode, if you're trying to set up something like Splunk, where you want to monitor all the traffic, then you want to capture all the traffic. So you want a copy of every packet regardless of where it's going, and that's what this special port is. This will let you have an extra copy of every packet, every frame coming out here, and that's called a mirror port. The problem is, of course, if you have a 24-port switch, say running at 10 gigs, if 23 of those are carrying real traffic, you only have one span port, and it can only carry 10 gigs, so it might not really be able to carry all the packets, all the frames, if all those guys are screaming really fast. So that's an issue. So a better solution is to get a special hardware device just for this purpose, a network tap, which will create an extra copy of all the traffic on a cable and send it off to your traffic monitoring device. These things are in fact pretty expensive. I tried getting a cheap one and it didn't work. Anyway, all right, then there's routers at layer 3. These are used to move from a local area network to a wide area network. You learn to span while setting up security onion. Yep, that's right. It's a big issue with setting up security onion or any other monitoring solution, is where do you collect the traffic and how do you get the traffic? Anyway, so routes, the original routes had static routes. The original routers, the early thing, because you have a simple problem. For example, your home network. You only have one route, the default route to go to the internet. So you just type an IP address in the default route of your router, and that's it. That's simple enough for small networks, but on complicated networks, it's different. This is what a home network would look like. You have a router here. This is wired up the way it used to be wired up with computers and a hub, but nowadays this would all be your router with a switch. And to connect to the internet, so it would have a public IP address to go to the internet and a private IP address to go inside, and you'd assign dynamic IP addresses to your clients in here, and all of them can share one public internet connection. And the router runs at layer 3, and it lifts them off the 192.168 network and drops them on the real public internet with a real public IP address. So all the servers on the internet think that all these devices are sharing the same IP address. So then there's routing protocols. If you have a larger issue, like a big company with several locations, then you've got a more complicated routing situation where you might purchase various T carriers, and these routers will have to decide how to reach. If I did it in Office A and I want to send it to Office C, I could send it this way, or I could send it that way, or other ways. And so the router has a decision to make of what is the best way to send the traffic. And if a wire breaks or I add another device, then it has to dynamically adjust the routing table to again learn all the new routes and make intelligent decisions of the best route. And that's what a routing protocol does. It sends traffic through the network that tells the routers what routes are available, so they can have an updated routing table and decide where to send the frames, or where to send the packets. Let me say it's packets at layer 3. So the earliest one was RIP, the earliest routing protocol. That was slow and inefficient, and a better one is OSPF, a more modern one. These are interior protocols used for internal networks like from the same company. And if you go to the internet, everybody has to use BGP, which is the one that moves you between ISPs and between nations and countries and cities, all the big hops. So the routers don't know the whole network. In distance vector routing protocols like RIP, the router does not know the whole network map. It just knows a distance. Like AT&T is 2 hops out here, CISSP is 3 hops out there. That's all. So it's a very basic protocol from the early days of the internet when the routers were very slow, weak processors, not much memory. And so this tended to make the wrong decision. It didn't even know enough to favor a route with a higher speed connection. It just counted the number of hops, which is the number of routers you pass through, and considered a shorter number of hops to be the better connection. So it would sometimes choose the slower route instead of the faster route, and sometimes it would get confused and send packets the wrong way for minutes at a time. It was not a very efficient routing protocol. You'd have routing loops where it would do something like this. I'm trying to get somewhere, but all it does is it makes a few hops, and then it starts going to 101, 103, 101, 103, 101, 103, because these routers are confused. It sends it over there, and that guy thinks it should send it back, and you just go back and forth instead of getting anywhere. It's the kind of stuff that can happen with RIP. If you leave the network alone for like 10 or 15 minutes, it will eventually stabilize, but it can spend considerable amounts of time with errors in the routing table. So that's this old inefficient one called the distance vector, and you see it only updates the thing every 30 seconds and has a lot of problems. So there were a bunch of defenses put in, like split horizons, so it won't echo a route back to the router that originated it, and something called a poison reverse and a hold down timer to try to prevent the router from receiving an old update with out-of-date information and erasing the good information, which was a problem with these because the updates don't have like timestamps or anything. It was just a very primitive system, and almost nobody uses it anymore. Now they all use link state routing protocols because modern routers have enough memory to just know the whole network map. So the router knows the whole network map, and it can now make an intelligent decision of what the best route is, and it knows how fast each link is, so it's much better. But of course, your router has to be more powerful. And OSPF is the open source common interior protocol used for this. The routers get updates every time something happens that changes the network, and they all update their network maps, and they all know the complete network map, and they then can make intelligent decisions of where to send the packets. So it converges much faster, and much less time is wasted sending packets the wrong way. It's intelligent, but the network engineers sometimes have, BGP. It's easy to have BGP errors. There are a lot of them. And it's easy to have spoofing on BGP. China has done this, Russia has done this, and there's evidence that the NSA has done it. You can send out malicious BGP updates and reroute traffic to pass through you. So yes, the BGP can be messed with. They can all be messed with. All right, and that's BGP. Used on the internet, this routes between autonomous systems like ISP and large companies, and you know, like I say, there are flaws and errors in BGP also. There are various companies that watch these, and you can see them, but often traffic does pass it down the wrong route for some period of time because somebody is sending out false BGP updates, usually due to errors, but several times very suspiciously looking like genuine military attacks. All right, so 4H. I'll give it a few more seconds. I think we had 12 last time. Ah, yes, go lightly. Well, that was the issue of the internet. If we didn't have so many criminals and hackers and stuff on the internet, things would be a lot simpler. All right, I guess that's it. Okay, which one is at layer 3? Yep, router's at layer 3. All right. All right, what device moves packets from one LAN to the internet? Yep, that's routers again. All right. All right, which protocol used hop count as the metric? That was RIP. All right. Or what's the interior router protocol that converges rapidly? Yeah, that's OSPF, the replacement for RIP. All right. All right, now I know who this is. And that's a person that's won previously, but I never did find out who they are, so I think they're not enrolled, which is fine. And I know who that is. All right, good. Well, let me stop this recording.